are thousands of asteroids out there on the outer space. Many of them cross the Earth's orbit, and quite often, small asteroids impact the Earth, disintegrating and blowing up in our atmosphere. However, on rare occasions, some of them make it to the surface, and depending on the size, can cause catastrophic damage, as with the dinosaurs. Luckily, we can prevent that, because asteroid impacts are the only natural disasters we can prevent. But we are not yet there. To deal with such threats, a lot of prerequisites need to be prepared, and that is exactly what the NEOShield-2 project is working on.
To build up a deflection capability, one of the first major things to do is the implementation of a deflection test mission, to develop and demonstrate the technology readiness and to answer physical uncertainties which cannot be answered on Earth. A further justification for the test missions are the uncertainties in the asteroid deflection physics, which need to be proved by real measurements at and with an asteroid. At NEOShield-2, we have thought about how to achieve these demo mission objectives with an affordable yet effective mission concept, addressing all the required measurements and a flexible mission timeline. This is why we propose NEOTωIST, a novel concept making use of a simple mechanism.
What we're trying to do with this mission is change the spin of an asteroid using a kinetic impactor. From a technical point of view, there's three things that are really important here. First objective of a kinetic impactor demonstration mission is to basically prove that the technology to do the mission works, and what that means mainly is being able to hit the asteroid at very high velocity, yet very accurately, and that's not a totally trivial thing. To give you an idea, in the NEOTωIST mission concept, we're approaching the asteroid at about 8 kilometers per second. That's 8 times the speed of a rifle bullet. Clearly, you don't want to be doing that the very first time in a real threat situation, but you want to prove it beforehand. The second objective that we have is to really show conclusively that we've moved the asteroid and also how much we've moved it.
The reason we chose Itokawa is because it's already been visited by a Japanese spacecraft and measured the physical properties, the shape and the rotation rate of it. What we try to measure with the change in rotation rate is how much ejecta comes out. If there's a lot, you change the rotation rate a lot because it enhances the momentum that you give the asteroid. The results of the NEOTωIST mission would enable us to more accurately predict the outcome of a real emergency deflection attempt.
And that brings us kind of to the third objective of such a mission, which is to learn more about the impact physics. In order to do that, we have another small spacecraft, 2 actually, that separate from the impactor as it approaches the asteroid. We separate 2 small spacecraft before the impact. One of them goes onto a flyby trajectory. The other spacecraft that we have is what we call the chaser, and that's basically a small flying camera which is ejected from the impactor, let's say backwards, and it follows the impactor to the impact site with a certain delay. So it gets very close and potentially gets a very close-up look at the impact event and perhaps also the crater. I think it's an important problem for someone to work on. I don't think we'll need it tomorrow or next week, but I think there's not that much disagreement about the fact that someday it'll become important to have the capabilities that we're developing with this.